Welcome back everyone. My name is Pedram and this is where we do machine learning codes and concepts. Let's get started. All right, let's do module number 8, K-nearest neighbors. So KNN is a very simple machine learning non-parametric model which can be used both for classification and regression. And if the dimension of the feature space is small, let's say single digits, 2, 3, 4, 5, we are going to see that the KNN is very powerful as well, especially when it comes to classification. However, when the dimensionality of the feature space is large, something called the curse of dimensionality is going to kick in, and we will be better off using other machine learning techniques. But yet, this is a very simple and powerful model that we should have in our arsenal. So let's look into the details. Module 8, K-nearest neighbors. Okay, where we are. As you can see, KNN is a non-parametric supervised machine learning algorithm which is used for classification and regression. However, later on we're going to discuss that KNN is mainly used for classification. Okay, and it is a non-parametric model because we're not going to impose any functional form to the data. So we're going to do this module in 3 parts. In part 1 we cover KNN models for classification tasks. And basically we start with some definitions and we talk about the hyperparameters of the model, which is basically the choice of K and the distance metrics. K is simply how many of these observations do you want to have in a neighborhood. So here in this example, K is equal to 3, and then in the bigger circle, K is equal to 6, and etc., right? So that's a hyperparameter that we need to pick before training the model. And then the distance metric. So for example, in two-dimensional space, why are we using circles, right? So in the Euclidean distance, why are we using circles? Why not squares, right? So we're going to talk about those things. In part 2, we will cover the KNN regression, and we will compare it with linear regression. And there we're going to say that, okay, when it comes to regression, we should be careful that why KNN regression is not necessarily the best option. And we talk about a concept called curse of dimensionality, which we're going to cover in part 3. And then we're going to conclude this module by going over some pros and cons of KNN and its application in the finance. Okay, so let's get into the details. Part 1, KNN classification. All right, so what is KNN? K-nearest neighbor is one of the simplest and best known non-parametric supervised learning techniques which is mostly often used for classification, as we discussed it earlier. So the idea is to classify a new observation, let's say in the test set, by finding similarities. So this is a key term. Similarities, the nearness. Similarities between that observation and its k-nearest neighbors in the existing data set, right? So let's see how the process is done and how we basically do the KNN classification. So imagine this red circle is what we want to identify. What should be the class of that red circle? We have two classes, class A, which is yellow. This is our class A, and class B, which is purple. And imagine this is our simple credit default example. Here we have income versus monthly balance. And it seems that if the monthly balance is higher for people with lower income, the probability of default, let's say that most people are going to default. So let's say class B is default and class A is no default. Maybe those people that their monthly remaining balance is low and they have higher income, so there's a good chance that they're going to be classified as no default. Okay, so this is a setup. And imagine now you want to classify this red observation here, right? And you want to see should it belong to, so this observation with these features, with this level of, let's say, monthly income and this level of monthly balance, what should be the class of this observation or this individual, right? The choice of distance metrics as well as the value for K are the choices that and the analyst, you're going to make before running the algorithm. So these are the hyperparameters. So before you decide, so what should be the algorithm decide what should be the class for this red observation here, you have to pre-specify two things. Number one, K, what's the value of K? How many neighbors you want to see? in the neighborhood that you define, and then how you define that neighborhood. What's the shape of that neighborhood? So for example, in 2D, we say, let's say the shape of dimension is circle. In next slide, we're going to talk about the shape of this distance matrix, right? So here, for example, we're using Euclidean distance. And from algebra, you know that the Euclidean distance of a point, so let's say all these points in 2D have the same distance from the center, right? So we call it Euclidean distance. We're going to talk about the details of the distance metrics that we're going to use for KNN in the next slide. But let's say, okay, you pick two things, K, number of neighbors. Let's start with 3. And D, your distance matrix, is Euclidean. In 2D, it's a circle. Then you're going to say that, okay, if K is equal to 3, in this super simple example, what should be the class of red? So this new observation, the red circle, should be classified as purple, right? Because in this neighborhood, let me use another color. Let's use red. In this neighborhood, there are 2 purples and 1 yellow. So we do something like this. The probability of purple given that neighborhood, let's call it neighborhood 1, is going to be what? 2/3. And the probability that the observation is yellow given that neighborhood is going to be 1/3, right? So the model is going to look at these probabilities and assign class whatever has the highest conditional probability number, right? So the red observation is going to be classified as purple because there's 66% that in this neighborhood the observation is red, right? So as you can see right away, the outcomes of KNN classifications are going to be probability. So KNN, just like logistic regression, is another probabilistic model. All right, now KNN is going to be sensitive to the choice of K. So for example, if I go ahead and change the number of K, let's say if you want to increase the number of K to 6, then see what happens. Okay, so if we change the number of neighbors into 6, so this is our new K now, and then the new neighborhood is going to be defined as this circle, right? Now in this circle, when K is equal to 6, what do we have? The probability that the observation, the red in the test set, is going to be purple given the neighborhood 2 is going to be what? So we have 2 purples and 4, let's say yellow, right? So the probability is going to be 4/6. And the probability that that observation is yellow given neighborhood 2 is going to be 2/6. So the model is going to, for purple it's 2/6, the other way around, right? So purple is 2/6 and yellow is 4/6. So the model is going to assign class yellow to that red observation, right? So as you can see, if K is equal to 3, the outcome is going to be purple. If K is equal to 6, the outcome is going to be yellow. So this is the choice of K is going to be an important one down the road. And this is one of the hyperparameters that we're going to tune, use a method later on. We're going to talk about it. Okay. So I want you to focus that, and contrary to other learning algorithm that allows discarding the train set after the model is built, KNN is going to keep all those train examples in memory. So we say that KNN is a lazy learner. It means that the algorithm makes no generalization. And basically that means that there's a little training involved when using this method. And because of this, all of the training data is also used in testing when we are using KNN, right? So it is lazy because if you want to classify any new observation, so let's say you want to classify this green observation. So the algorithm has go from the beginning again and look at the neighbors. So for example, you start with 3 neighbors, so maybe do something like this and etc., right? So it's going to use the entire train set again for classifying every single observation in the new test set. So for that reason, we're going to call it a lazy learner. All right, now let's summarize what we discussed earlier in formal steps, right? So KNN can be used for more than 2 class classification. In this example, we have 3 classes, right? Let's say the data set has 2 dimensions, so 2 features, x1 and x2. So the dimension of the data is pretty basically nothing, right? Only 2. And then we have three classes. We have class orange, we have class blue, and class green. So one of the advantages of KNN for classification is that compared to other models is that it's going to be easily expandable to multi-class classification. So in this example, we're talking about three-class classification. And then let's say we want to identify what is the class for this new observation in the test set, right? So that's the goal. Now let's do it step by step. Step one, choose the number of neighbors, k. And this should be a positive integer, right? 1, true, and etc. So let's say k is equal to 7. Okay, and remember, we have to pre-specify these numbers before the model is able to generate some outputs, right? And later on, we can use those outcomes and then optimize these hyperparameters. So let's say we start with k is equal to 7. The second choice is, what is the shape of the neighborhood? Do you want to use a square? Do you want to use the circle in 2 dimension? What is the shape of your neighborhood, right? So we call it the choice of distance metrics, right? The distance metrics can be Minkowski, Euclidean, Manhattan, and etc. Let me give you a quick background for those of you who hadn't get a chance to watch our previous videos when we talked about norms. So there's a close relationship between norms and distance. And let me open up this distance metrics idea here. Let's say, for example, we're talking about Minkowski distance metrics, right? So the Minkowski distance metrics is defined as, let's say, d of x and y. So these are 2 points, x and y. And it's going to be defined as summation of an absolute value of xi minus yi to the power of p, and then the entire thing to the power of 1 over p. Okay. Now, depending on the choice of p, we're going to come up with different shapes or different distance metrics. Okay, let's say if p is equal to 1, what do we get? The distance matrix is going to be something like absolute value of xi minus yi. Of course, the summation of all those things, right? And to the power of 1. So what is this? If you have watched our previous videos, this is our Manhattan norm, right? Or here we call it Manhattan distance. Do you remember, if you want to go from point A to B, let's say this is point B, this is point A, we can go like this, right? This is one way, this is one way, right? So this is our Manhattan distance. If p is equal to 2, what do we get? If p is equal to 2, so here we have the summation of basically xi minus yi to the power of 2, and the entire thing to the power of 1 over 2, so which is square root of. So if you pay attention to this one, this is our Euclidean distance. This is L2 norm, right? So let's call it Euclidean. So in this very simple example, we're going to use Euclidean distance, right? So the shape of, in 2 dimension, the Euclidean distance is going to be a circle, and our Manhattan norm is going to be something like this, right? Manhattan distance. So let's say most of the time, if you're going to use Euclidean distance for KNN classification, unless we have lots of dummy variables in the data. So we're going to talk about those things later on. So if there are very categorical variables in the model, then the distance metrics, the choice of distance metrics is going to become a little trickier. But right now, let's say, okay, step number 2, we chose that our distance metrics is Euclidean. So we're going to talk about the circles. Okay, guys, remember the goal was to identify what should be the class for this new red cross in the test set, right? By looking at the observations in the train set. So if you use the Euclidean distance, and when k is equal to 7, this is going to be our neighborhood. So let's define it as neighborhood null, right? Then we're gonna, what is the next step? The next step is to basically define these neighborhoods and calculate the conditional probabilities, right? So this is our neighborhood. Let's call it n null. And next step, let's calculate the conditional probability. So here, let's do them manually very quickly. So we're going to say that, remember, we are going to have 3 classes, orange, blue, and green. And we need to calculate the probability of that y, this is our y in the, belongs to any of these classes, right? So here, j can be those 3 classes by looking at the features in the test set. So what are the features in the test set here? So this is going to be, let me use red. This is going to be, let's say, x2. This is going to be the feature for x1. We want to see that an observation with these two features, what is the class? Is it going to be orange? Is it going to be blue? Or is it going to be green, right? So for that, we need to calculate the conditional probabilities. And that's very simple. Basically, we look at each neighborhood and conditioning down on that neighborhood, we're going to count these the observations, right? So let's start with conditional probability that the class is orange. So probability that class is orange, let me show it with org, given X is our X in the test set. So this test set is our red cross. Let me just put a red cross here. You realize that's what we were talking about. Okay. So if I ask you, okay, in that neighborhood, can you calculate the conditional probability? What is your answer? So how many observations do we have? We're going to have 7 observations, right? Because this is the way we define the number of neighbors. So we have 7 observations. So 1, 2, 3, 4, 5, 6, and 7. And if you calculate the conditional probability of orange, so what do we get? 3 out of 7, right? So it's going to be 3 out of 7. Then what is the probability that y is equal to blue given X? As you can see, there are 4 blues out of 7, right? And then finally, what is the probability of y is equal to green given X? So how many green observations do I have in this neighborhood? 0. And then when we're done with conditional probabilities, we're going to classify that new observation in the test set to be the class with the largest probability. So here the answer is going to be blue. So this observation is going to be turned blue by the algorithm. So this observation is blue. Okay, so these are the steps for KNN. And as you can see, this is a very, very simple model to work with, right? So this is the advantage of that, and we're going to talk about the pros and cons later on in the third part. Okay. Now that we know how KNN algorithm is doing the job and how it's able to classify the new observations for us, let's talk about a concept called decision boundary. We're going to look at the very simple example in 2 dimensions and visualize this decision boundary in 2 dimensions. And we will explain what do we mean by that. But let's first set up the scene. Okay, so here in this very simple example, we're going to have 2 classes, blue and orange. So this is class blue, this is class orange. And as you can see, the data is only 2 dimension. So the dimension of the data is very small. The black cross is a test observation. So at the end of the day, we want to see what is the class of this black cross. So let's say k is equal to 3. And if k is equal to 3 and the Euclidean distance is used as a distance matrix, then the black cross is going to be classified as blue. I think we can see it from this neighborhood, right? So we have 2 blues and 1 orange, so the probability is 2/3. So the class for this, let's say, a black cross is going to become blue. All right. And we're going to repeat this process for every single potential element in the feature space, right? So guys, this is in order to just visualize this decision boundary. We don't necessarily need to do that, but just for the sake of argument, let's try to recalculate this process for every single, every potential points in the feature space. So what do I mean by that? Imagine, we have these values for x1, these values for x2. We can have a mesh, right? So we can have a mesh like that. And then we can basically look at every single observation in this feature space and decide what should be the class, right? As you can guess, so if I'm here, if I'm somewhere here or here or here, whatever, these are going to be most probably classified as blue, right? Because in this neighborhood, everything seems that to be blue. This is because if k is equal to 3, then all these observations are going to be classified as blue. They're closer to these 2 blue observations, right? Or basically here, these are the blue ones. So as you can guess, if you repeat this process for all these potential observations in the feature space, they're going to be blue, right? So these are easily, we can see that they're going to be blue. And for example, these are going to be orange. And maybe these are going to be orange, and etc. Now let the computer does the job and see how the decision boundary is gonna look like, right? Okay, so this is at the end of the day how the decision boundary is gonna look like. So all the observations here are going to be classified blue, all the observations here are going to be classified orange, and here are going to be classified blue, right? So basically, the KNN decision boundary is shown in black, right? So this is our decision boundary. This means that the blue grid indicates the region in which the test observation will be assigned to blue, and the orange grid indicates the region in which the test observation is going to be assigned to orange. And as you can see, this classifier, this decision boundary, this black line, is very, very nonlinear and flexible, right? As you look at that, this is very flexible, and it is obvious that it's nonlinear. It can be super flexible because remember, KNN is a non-parametric model, so we are not imposing any functional form now on the model, right? So this is going to be both advantage and disadvantage, and we need to, based on, depending on that level of K, we need to tune this hyperparameter. Okay, basically we're going to talk about how smooth or how complex is the decision boundary. But in this very simple example, you're seeing that the KNN classifier is doing a very good job, right? All the observations in this example, at least in the train set, are classified perfectly, and we hope that when we throw the test observation to this decision boundaries, they're going to be classified correctly. Now, if you compare this decision boundary with what we covered in logistic regression, remember, in logistic regression, let me use the color green. If I want to come up with a decision boundary and use a linear logistic regression, maybe we get something like this. All right, so this is our logistic regression classifier. And so if we do it that way, well, we call everything to the left, let's say class blue, everything to the right, class orange. We're going to have a couple of misclassifications here, right? And we can also work with different versions of logistic regression, combine it with polynomial, make it curve a little bit. Maybe we do something like this. But eventually, as you can guess, in this very simple example, logistic regression is not doing a good job. Why? Because the data set itself was nonlinear. Look at that. We have a couple of blues here, blue here, and orange here, orange here. So whenever the data set, the structure of the data set itself is nonlinear, then a nonlinear model, a non-parametric nonlinear model like KNN is going to do a better job. Okay, we're talking about KNN classification, and we already know the classification performance metrics from part 19. If you haven't watched that video, please make sure that you watch it and then come back to this one. Okay, so what are the standard classification performance metrics? We know that all these metrics are going to be based on something we call it the confusion matrix. This is our confusion matrix. And we are going to have, so here, this is our confusion matrix, and we can construct, the different performance metrics off of that matrix, right? Let's say error rate, accuracy, precision, recall, F1 score, MCC, and etc., right? We covered all these things in the previous video. Okay, so now, for example, let's look at the error rate. So error rate is going to be defined as 1 minus accuracy. Basically, and this is the way that we define accuracy. If you remember, we define accuracy like this: the good numbers, true, negative, true, positive, divided by the entire observations, right? True, negative, true, positive, false, negative, and false, positive. And of course, the error rate is going to be 1 minus the accuracy. So basically, for error rate, we're going to focus on bad numbers and count them. So false positive and false negative. So as you can, and divided by the entire size of the, let's say, the train set, or if you're looking at the test set. So this is how we define the error rate. If you want to do it manually, and then if you want to do it straight, we say 1 divided by number of observations, and basically counting the misclassifications, right? These are the false positives and false negatives whenever the prediction is different from the actual, right? And as you can guess, a good classifier is the one that it's working in the test set, right? The test error is the smallest, right? Not necessarily the train error. So we know that with KNN, we can change the value of K such that the model can be super flexible. And as you can see in the previous example, the number of misclassifications was 0. So basically the error rate in the previous example was 0. But that's not what we should look into. We should look at the test error in the test set, not the train set. All right. And like any other classifier, if the data is highly imbalanced, which most of the data sets in finance, basically, when it comes to the loan applications, credit card default, and etc., in the examples like this, the data is imbalanced, right? Then if that's the case, we should use F1 score, precision, or recall instead of the error rate or accuracy. Or if you want to use all the information from confusion matrix, you can report MCC, right? So this is what we covered in the previous slide, in the previous part 19. The Matthew correlation coefficient. Okay, one last thing I want to emphasize and I want to mention about the performance metrics using KNN is that the outcome of KNN, let me write it down, the outcomes are probabilities. Let's say it's 33%, let's say it's 40%, and etc. So this is a probabilistic model. It means that, let's say 80%. At the end of the day, we can define a threshold, right? Let's say if that threshold is equal to 50%, then we say anything above 50%, the answer is, let's say, class blue. Anything below 50%, let's call it class red, right? So this matters because if the outcome of your classifier is probabilities, you can basically plot true positive rate versus false positive rates, and we can come up with our ROC, right? So imagine this is the true positive rate, this is the false positive rate, and if the idea is that this is a model with no skill, so the model with no skill, if you calculate the area under the curve, is going to be 50%, right? So this is a random model, 50%. And your KNN better be somewhere here. Let's say the area under the curve is, I don't know, more than 50%. Your model is doing something better than just chance, pure chance, right? So we can do something like this with KNN because the outcomes are probabilities. So this is important. KNN is one of those classifiers that, just like logistic regression, the outcome is probabilities. We call them probabilistic models. All right, let's conclude the KNN classification part 20, by talking about how we tune the hyperparameters. So the hyperparameters in KNN were the choice of distance metrics and choice of K, right? So for the distance metrics, most of the time we use Euclidean distance. And unless if you have multiple categorical variables in the data, and then the choice of distance metric is going to become important. Otherwise, we're going to by default always use the Euclidean distance. So now let's talk about choice of K. So basically this K is something that basically navigate us how we can deal with the bias variance trade-off, right? So let's start with the very flexible model. When K is equal to 1, remember, those neighborhoods, those circles are going to be very small and basically include that observation, that specific observation in the train set, right? So the model is very flexible, and when the model is very flexible, we're going to see that the algorithm is going to be able to capture the pattern in the data on average. So that's why the bias of the model is small. But on the other hand, the model variance is going to be large, because if you use yet another data set, if you use another random subset of the data, we're going to see that the model variance is going to be high. So this is the case where K is equal to 1. Let's say this is a very simple two-class classification. There are classes blue and red. And as you can guess, the decision boundary is very flexible. Let me actually use color black. It's very flexible, and at some point it's somehow funny too, right? It's obvious that we are overfitting in the data here, but let's say just for the sake of argument, yes, if the K is equal to 1, the model is very flexible, and as you can guess, the number of misclassification in the train set is going to be 0. So the error rate is 0, the accuracy is 100%. Then we're going to make this model less flexible, less complex, by increasing the value of K, right? So as K grows, the model is going to become less flexible. This means that the decision boundary is going to become smoother. It's not like this, at least when we see for the K is equal to 1. So this corresponds to a low variance but higher bias, right? So maybe on average, we are not capturing the pattern in the data, but the model variance is going to be smaller. Now, if we keep increasing the number of K, so let's say K is equal to 9 here, And as you can see, the decision boundary is going to become smoother and smoother. So for k is equal to 5, we have something like this. For k is equal to 9, it's going to be smoother. And now let me ask you a quick question. What if k is equal to the number of train observations, right? So let's say here we have, in this example, we have 36 red. So there are 36 of these red dots and 30 of these blue dots, right? So overall, n is going to be equal to 66. So what if k is equal to 66? What do we get? What's the outcome of the model? So I leave it as an exercise. So I want you to, just comment, write your answer in the comment section. So what will happen? The number of k is equal to the number of observations in the train set. What is the outcome of the model? All right. So how do we define what is the optimal value of k? So we can plot for any level of k, we can plot what is the error rate, right? So when k is equal to 1, what is the error rate? When k is equal to, let's say, 10, what is the error rate? And so here we're going to plot the error rate versus 1 over k. So we can plot error rate versus k as well. It really doesn't make a big difference, but in practice people tend to do it this way because we want to say if we go from left to right, the model is more complex. As you can guess, when k is equal to 1, then 1 over k is equal to 1. So this is the most complex model when we are standing here. And let's say here k is equal to 100. This means that 1 over k is equal to 1%, right? This is, in this example, let's say we are investigating if k is equal to between 1 or 100. 1 and 100. Then we can plot the error rates for two sets, right? First for the train set and the second for the test set. We can calculate the train errors. So let's say the train errors are these green ones that we calculate for different values of k, and the orange ones are the test error. So which one should we focus? Yes, the answer is test error, right? Because we don't care how good or bad the model is doing in the train set. At the end of the day, we want to test the model on something that it hasn't seen before, right? So we want to test the model on the test observation, right? And on the other hand, we know that in practice, we can make the model super complex by setting k is equal to 1. And the error rate in the train set can be always 0. So this is the error rate in the train set. Can be 0 if k is equal to 1, because there's going to be no misclassification. If I had another red observation here, this should be the decision boundary. If I have another observation here, then this adds to the decision boundary. As you can see, this is super complex, right? And so that's why we don't care about this green curve here. We don't care about that one. What we should focus on is the test error. So we should focus on this one. So we can plot the test error versus k. And at the end of the day, we get something like this. And we see where that error rate is minimized, right? So this is, let's say, the error rate here is minimized at this point, right? So this is the point that error rate is minimized. And actually, for the sake of argument, I'm going to claim that, okay, there are 2 points here. Well, let me actually simplify it. Say, imagine this is, okay. So there are 2 points that the model is going to give you the smallest error rate, right? Then you want, first of all, let's see what are those points. So here k is equal to 10. If k is equal to 10, then 1 over k is 1/10. And here, we know that here the k is equal to 20 because 1 over 20 is 5%. And I'm just making up these numbers. Imagine here k is equal to 17. Okay. So at the end of the day, we know that at k is equal to 10 and k is equal to 17, the error rate is the smallest in the test set. And let's say this is the number, and that number is 0.13. Which one should we pick? Is k is equal to 10 or k is equal to 17? What do you think? Yeah. We always go with a model that is less complex, right? So if you get the same performance when k is equal to 10 in the test set and k is equal to 17, we pick the model which is less complex because we don't want to necessarily make the model unnecessarily complex, right? So which one is the simpler model? K is equal to 10 or k is equal to 17? Yes, this is the simpler model, right? When k is equal to 17, we are here. So we say that, okay, the answer is k is equal to 17. And this is how we used this method in order to figure out what is the optimal value of k. And one last thing, that in practice, we prefer to work with the error rate in the cross validations, right? So we prefer to report the cross validated error rates and then plot that curve versus 1 over k, right? So maybe we get something like this. Maybe we get something like this, and maybe the minimum is here or here, whatever. But this is what I want you to pay attention, that in practice, we prefer to plot the cross-validated errors versus k, or 1 over k. Part 2, KNN regression. All right, now let's see how KNN regression works. So let's visualize KNN regression line in 2 dimension, right? And for that, we're going to work with a very simple example. There is only one feature, x, and this is our target variable y. And imagine x and y are discrete variables, right? So it can take 1, 2, 3, and etc. This is just for the sake of argument, and in order to simplify the calculations, we can do it manually. At the end of the day, the KNN regression method is very, very closely related to the KNN classifier. This means that we need to come up with the hyperparameters, pre-specify them, like say, what is k, is it 1, 2, and etc., what is the distance matrix, and etc., right? And the predictions are going to be the average value of the target variable in that specific neighborhood, right? So this is very simple. Actually, it's simpler than what it looks. So let's look at an example. Imagine we start with k is equal to 1. I'm going to say, use red color, k is equal to 1. And as I said, the values for x, the observations can take discrete values, 1, 2, 3, up to 13, right? Imagine we want to sort from the very right-hand side. Let's say we want to see what is the prediction of the model when x is equal to 13, right? So when x is equal to 13, then the prediction of the model is going to be equal to what? The f hat is going to be 1 divided by k, which is 1, the summation of, in that neighborhood, yi's, right? So what is, if I say that, okay, here, this is point 13, let's say in this neighborhood, so what is the value of y? The value of y is going to be 2, right? So this is going to be 2, so the answer is going to be 2, right? So if x is equal to 13, then the prediction is going to be 2. If the number of neighbors is 1. If x is equal to 12, the prediction is going to be 2 again. If x is equal to 11, the prediction is 2. If x is equal to 10, what is the prediction? Yes, the prediction is going to be 5. Why? Because when x is equal to 10, then we look at the neighborhood. Let's say this is how we define the neighborhood. And the closest observation, well, let's do it this way. This is from 10, this is the neighborhood, and the closest observation in that neighborhood is this, and the value of y in that neighborhood is 5. So this is what's the prediction is going to look like. The prediction is going to be 5. If k is equal to 9, again 5. If k is equal to 8, okay, now if k is equal, sorry, not k, if x is equal to 8, then look at that. If I want to say, it seems that the distance from this point, let me use green, the distance from this point and this point are the same when x is equal to 8, right? So we can say, okay, the model can randomly pick one of them. Let's say the model pick this one, so the outcome is going to be, again, red. But when x is equal to 7, this is the outcome. The prediction is going to be 8, and etc., right? So it's going to remain 8 here, and then here the same story. Let's say randomly the model select this one, and then when x is equal to 2, this is a prediction. X is equal to 1, this is a prediction. So it seems that we get something like this. So this is our regression line when k is equal to 1, right? Now, let's look at another example. What if k is equal to 2? For that, I'm going to use green. So if k is equal to 2. So if x is equal to 13, so the first closest two neighbors are going to be these two. And the model is going to do something like this. K is equal to 2. So the f hat for x is equal to 13 is what? Is 1 divided by 2, and the summation of all those y's, right? So what are the y's? So I have this is y is equal to 2, y is equal to 5. So 2 plus 5. So 7 divided by 2, 3.5. So this is what the model predict. So 3.5. If x is equal to 12, the same story. For 11, the same story. For, let's say, 10, we're still here, here. And then when x is equal to 9, actually, when x is equal to 9, then the closest neighbors are going to be, so this observation is the distance is 2 from left. If I go 2 from right, okay, so the closest, actually, when x is equal to 9, the prediction is going to be 5 plus 8 divided by 2, right? So we get 6.5. So here, if x is equal to 9, we get, let's say, 6.5, right? All right, when x is equal to 8, then these are the same number. The closest observations are this one and this one. So the prediction is going to be the average of 8 and 5. When x is equal to 7, then the same story, because these are still the closest numbers. When x is equal to 6, here, so we have, well, actually, these two are going to be the closest. So 8 plus 8 divided by 2, we jump up here. So as you can guess, this is the same for x is equal to 5. Let's look at x is equal to 4. For x is equal to 4, then the closest observations are going to be this one and this one. So it's going to be 8 plus 6 divided by 2. So the answer is 7. So we come down here. So 7, 7. I think we're going to remain here for the rest of them, right? So when k is equal to 2, we get something like this. And then here we went up, I guess. Yeah, here we went up. And then we came down. So this is for k is equal to 2, right? So this is a regression line, right? And as you can see, it's flexible. Like classification, KNN for regression is also very flexible and nonlinear, as it is obvious here. So you can think of, expanding the idea of k. So what does the regression line look like when k is equal to 3, and etc. So in this very, very simplistic example, actually I want to show you a very cool exercise. We know that n in the sample set is 5, right? So let me label them. This is point A, B, C, D, and E. So there are only 5 points, right? And if k is equal to 5, then what will happen? So basically, the prediction is going to be always one number, and that number is going to be the average value of all these y's, right? So what do we have? We have 6, this one, plus 8, plus 8, plus 5, plus 2, the entire thing divided by 5, right? So if you do the math, you should get something like 5.8. So when k is equal to 5, the model is always predicting this. So when k is equal to 5. And of course, this doesn't make any sense when k is anything greater than 5, right? So as you can see, just like the classification, when k is small, when k is equal to 1, the model is most complex. And the regression line is going to be more ragged, right? Unsmooth. When k is equal to 5, in this example, this is the least complex one because k is equal to the number of observations in a train set, and the model is going to always predict one number. This is the simplest model, right? Basically, it's equal to y bar. All right. Now that we know how KNN regression model works in practice, let's talk about how we tune the hyperparameter k, how we optimize that number to deal with the bias variance trade-off. Okay, so just like the classification, when k is equal to 1, the model is very flexible, it's very complex, and in that case, we know that the model bias is going to be small. On average, we're going to hit the target, we're going to capture the pattern in the data, but the variance is going to be large. We say that the model variance is large. It means that if you repeat this exercise with just another subsample of the data, the model is going to change. You know, the f hat is going to be different, right? The predictions are going to be very volatile, right? So this is when k is equal to 1, and not surprisingly, you know, we know how these things are calculated now, right? So it's the regression line is going to go through all the observation, and for that reason it's going to be very flexible. Okay, we know that the model variance is super high now. Now, as k grows, we deal with a less complex model, and the regression fit is going to become smoother and smoother. This corresponds to low variance and high bias. Okay, so let's say k is equal to 10, and as you can see, this regression line is smoother now, but it's still, compared to linear regression, is going to be very, very, very jagged, right? It's go up and down. Okay, then let's say k is equal to 50, so this is a lot smoother than compared to k is equal to 10, right? Now here, we talked about an exercise in the classification. Let's repeat that exercise for regression as well. Let's say k is equal to, let me use green. What if k is equal to the train size? So let's say the data in the train size is, I don't know, in this example, let's say we're talking about 300 of these blue circles, right? If that's the case, what is the prediction? What is y hat? How does the regression line look like? Okay, so I'll leave it as an exercise for you. Then let's see how we can optimal the value of k. So we're going to report the RMSE versus k, right? So now in this example, because I'm using k and not 1 over k, as we go from right to left, the model is going to become more complex, right? More complex, because we're reporting k. In classification, we looked at an example that we were looking at error rates compared to 1 over k. But here we're looking at RMSE versus k, right? Then I'm going to plot two things here. RMSE cross-validated version and RMSE in the test set. We are not interested to report the RMSE in the train set, right? Because we know that the RMSE in the train set is going to get closer and closer to 0. Okay, look at this one. Let me use red color. So if I report the RMSE in the train set, well, the model is capturing all the nuances up and down because it's super complex. The RMSE is going to be very small. So we know that if I want to plot the RMSE in the train set, it's going to be something like this. Always converges to 0. So there's no point of doing that, right? We're going to report RMSE in the cross-validated version and the test set and plot it versus k, right? And this is how it's going to look like. And as you know by now, we most of the time look at the RMSE cross-validated version when we want to tune the hyperparameters, right? So let's say that's the case, and this RMSE is minimized at this point, and at this point, let's say k is equal to 3. Okay, so we get the optimal number here, and this is our RMSE cross-validated version. Okay. If you're curious to know why I prefer to use the RMSE cross-validated version versus RMSE test set, I encourage you to watch our part 6, where I talked about cross-validation in machine learning in general. But the short answer is that, the cross-validation is used for tuning hyperparameters because we need to use the validation set to optimize the parameters, and at the same time, we want to report the performance metrics in the test set on the data that the model has not seen before. So the answer is going to be cross-validated data. And another important reason that I prefer to use cross-validation versus test set is that what if the test set is small, right? Then we know that if I do 5-fold cross-validation, we can report the RMSE and the standard error of RMSE using cross-validation. So I know that, for example, RMSE, let's say in this example, we're going to say k is equal to 3, then RMSE in the test set, let's look at the brown line. So let's say this is the RMSE. RMSE in the test set, let's say it's, I don't know, maybe 55. And RMSE cross-validation is going to be equal to 62, right? We know that RMSE in the test set, maybe in this example, is smaller, but this is one number that I can get by looking at the RMSE in the test set. However, if I calculate the RMSE in the cross-validation, depending on what is the k-fold, let's say we're looking at 10-fold cross-validation. So I have 10 of these numbers. I can report the standard error of the RMSE. This is going to be a lot more informative So I have two statistics now, right? The standard error and the average. Let's say the average is 62 and the standard error is some number, I don't know, 3. Then this is a lot more informative comparing to when I have only one statistic in general. So I prefer to report the not only for KNN model, for any other machine learning model, when I want to tune the hyperparameters, I prefer to use cross-validation and report the cross-validated performance metrics. Let's say the RMSE in the test set for classification accuracy, the cross-validated RMSE, cross-validated accuracy, and etc. All right. Now let's look at KNN regression in 3 dimension. Now we have x1, x2, and our target variable. Okay. So the same story, when k is equal to 1, the model is very flexible, low bias, high variance. As k increases, the model becomes less flexible and the regression fit gets smoother and smoother, and this corresponds to a low variance and high bias. So I want you to think about, pause this video and answer these questions. So one of them, in this example, one of them k is equal to 1, for the other one k is equal to 10. So I want you to tell me in graph A what is k, and in graph B what is k. Okay. All right, so I hope you got the right answer. So here k is equal to 1. If you see, the regression surface is going to be very flexible, goes up and down. And this is k is equal to 10. So the regression surface is going to be less flexible and it's going to be smoother. Okay. All right. Now let's conclude this episode by comparing linear regression versus KNN regression. Okay. Imagine the black curve is the true relationship between y and x. So we know that the true relationship is linear. Okay. In general, the true relationship is not observable. This is what we are trying to estimate. But let's say, for the sake of argument, this is a true relationship. Okay. And the green dashed line is going to be the MSE in the test set when we use KNN, right? So let's say we are going to report the MSE in the test set, and not surprisingly, we are interested in the performance of the model in the test set, right? Not necessarily in the train set. And let's plot the MSE in the test set versus different values of k, and we're going to report these numbers as 1 over k. So this is going to be the most complex model when k is equal to 1. And here, so for example, k is equal to 1 divided by 5, right? So k is equal to 5, is equal this is 0.2, and etc., right? So this is the most complex model, most complex. And the green dashed line is our MSE for the test set for different values of k, right? So if k is equal to 1, we are here. We know that the performance of the model in the test set is the worst, right? The MSE is the maximum here. Why? Because the model is unnecessarily complex. And let me actually try to show you that regression line here. Let's say this is if k is equal to 1, right? The regression line is going to be something as funny as this one, right? So it's going to be basically it's capturing noises, right? So when k is equal to 1, we know that the performance of the model in the test set is going to be the worst in the test set, right? Because yes, the model may be the bias is going to be small because on average we're hitting at a target, we capture the pattern, but the problem is that the model bias is going to be very large, as you can see. And when that's the case, the MSE, which is a combination of model variance and model bias, is going to be very large. So we are here. Then as we increase k, we go to the left, right? So as we increase k, we go to this direction, and it seems that the MSE in the test set is going to decrease. Okay, so this is how the MSE in the test set is going to look like for different values of k. Okay. Now, what is the black dashed line? The black dashed line is the MSE in the test set when we use OLS. So if I use OLS, this is, let's say the MSE in the test set is 0.9. MSE in the test set for when we use OLS is 0.9. And of course, not surprisingly, it's independent of the value of k, right? Because we are using OLS, has nothing to do with k. So we're going to get one number, and that one number in this example is, well, not 0.1, 0.09. It's 0.09, right? So it seems that when the true relationship in the data is linear, KNN, regardless of the value of k, is not performing as good as our simple OLS, right? So KNN is going to always do a worse job compared to a simple OLS when the true relationship is linear. Now, what if the true relationship has become more and more nonlinear? So what does that mean? So the more nonlinear true relationship, the better performance of KNN compared to OLS. Let's look at another example. So imagine here the true relationship is this curve. This kind of S curve is a true relationship. And now for some values of K, specifically for these values, KNN is outperforming the OLS, right? Because look at that. So it seems that, let me use my laser. So it seems that for these values of K, the MSE in the test set for KNN is smaller than the MSE in the test set when we are using OLS, right? So in this region, when K is equal to between these two numbers, so KNN is outperforming the OLS. Why? Because the true relationship was more nonlinear. So if you make the true relationship even more nonlinear, so let's say we have something like this, right? And then it seems that for any values of K, the KNN is outperforming the simple OLS by a large margin, right? For different values of K. So at this point, you might get excited and say that, wait a minute, why don't we use KNN as a regressor all the time compared to OLS? Because look at that, when the data is nonlinear, KNN is doing a very good job compared to OLS. So what do you think about that? You might want to say that, okay, so KNN is a non-parametric model, right? Non-parametric means that we are not imposing any kind of functional form to the data. So it can be as flexible as possible. And yes, that's the case if the true relationship in the data is nonlinear, then non-parametric models are going to do a better job compared to parametric models like OLS, right? Because imagine this is our OLS regression line. Okay. However, be very careful, guys. Here, the dimension of the data is only 1. And yes, if the dimension of the data is 1, and if the true relationship, for whatever reason, you know that the true relationship is nonlinear, then you might want to use KNN as a regressor. But in real world, in most applications, we are dealing with the data in very high dimensions. Let's say dimension is 100, 200, 1,000. And then when that's the case, the KNN is going to do a very poor job because of the curse of dimensionality. Okay, so here's the last part, part 3. Let's talk about curse of dimensionality and KNN pros and cons. So what is curse of dimensionality? The curse of dimensionality is a problem with the relationship between dimensionality and the volume. Okay. So basically, when the dimensionality increases, the volume associated with that area also increases, but not fast enough. So basically, we can say it like this. The sparsity of data happens when moving to higher dimensions, right? The volume of the space represented grows so quickly that the data cannot keep up with that and thus becomes sparse. So let me give you an example in 1, 2, and 3 dimension. So let's say, let's start with 1 dimension, the simplest one. Okay. So let's say the dimension of the data is 1. So let's say d is equal to 1. And just for the sake of argument, our x variable is discrete, right? So this is the discrete random variable. And it can, so let's say, how many observations here we have? So let's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the dimension is 1, and this random variable can take 10 values. So the number of observations. So what is the number of required observations? So I call it the number of required observations to basically span the entire space here. So the answer is going to be 10. If I have 10 observations, and assuming that the data set is just the random variable is discrete, then I only need 10 observations to span the entire dimension, right? So as we go from 1 dimension to 2 dimensions, let's say here we have x1 and x2. So dimension goes to 2, from 1 to 2. So as dimension goes from 1 to 2, then how many points do I need to span the entire feature space here, right? Again, just for the sake of argument, assume that both x1 and x2 are discrete and they can take 10 numbers. So the answer is going to be that 10 to the power of 2. So we're going to require 100 observations, in this example, hundreds of blue and red, to span the entire feature space, right? So as you can see, when the dimension goes from 1 to 2, the number of observations required to span the entire feature goes from 10 to 100. Now let's go to dimension is equal to 3. So in order to span the entire feature space here, how many observations do we require? Yes, 10 to the power of 3, right? So the answer is 1,000. So as you can see, this is growing so fast. Simply when I go from dimension 2 to 3, it went from 100 to 1,000. Then you can imagine, what if dimension is only 10? This is very small number for machine learning models in general. If you only have 10 features, you're gonna need 10 to the power of 10 or 10 billion observations to basically span the entire feature space. So as you can guess, this cannot keep up with the increase in the number of dimension, right? So we are going to end up with some sparse data, right? A sparsity in the data. Let's say here we have a sparsity in the data, here we have a sparsity in the data, and etc., right? So in short, what is the curse of dimensionality? We can say by adding extra dimension, the data points needed to cover the entire volume increase exponentially. So this means that the data structure and correlation in low dimensions does not apply or generalize well in the high dimension space. We call this problem curse of dimensionality. Okay, now let's talk about curse of dimensionality when we are dealing with the KNN models in general. Let's start with the classification model. So imagine there are two classes, red and green. And then we're looking at the data sets in 3 different dimensions, 1 dimension, 2 dimension, and 3 dimensions, the ones that we can visualize, right? So if the dimensionality of the data is only 1, then finding neighborhoods that in those neighborhoods there are observations is not difficult, right? We're not dealing with a no nearby neighborhood, right? So whatever, imagine here, wherever we are, if you pick at any level, any value for k, you're going to find some neighbors close enough to that observations, right? So when dimension is 1, most probably we're not dealing with the sparsity of the data. When dimension is 2, well, we're going to start seeing these curves of dimensionality, right? So let's say we are here, okay, then we define k is equal to 2, then the closest 2 neighbors are here, so maybe no problem there. Maybe the characteristic of this observation is close enough to the class green. But what if we are here? Okay, let me use another color. Let's use light blue. What if we are here? This is an observation that x1 is equal to, let's say, 1, x2 is equal to 1, right? And so in order to reach out to the closest observation, we have to expand the radius of that neighborhood, right? So we have to travel too far. Let's say we have to travel too far in order to get access to the first neighbor. So let's say this is the first neighbor is green. The problem here is that maybe this observation here, in terms of characteristic is not similar enough to this observation, right? So this is the idea of curse of dimensionality and dealing with sparse data, right? So it seems that here we will see no nearby neighbors. So that's the problem. And as we go to higher dimension, this problem is going to become more exaggerated. Okay, so that was an example for classification. How it's going to look like for regression? And in order to just quickly remind you what these curve means, so let's say the black dashed line is going to be the MSE in the test set using OLS. And it's going to be one number, right? And it's independent of the value of k. So the vertical axis is MSE in the test set. The horizontal axis is 1 over k. So for different values of k, we're going to get different numbers for MSE in the test set, right? And here we're going to look at different panels, right? So let's say p is equal to 1 versus p is equal to 20, and this is the dimensionality of the data. So dimension is equal to 1. Here, dimension is equal to 20. So we have 20 features versus 1 feature versus 2 features, 3 features, and etc. So for any of these data sets, we're going to use linear regression and compare it to KNN regression with different values of k. And let's see how it's going to look like. So it seems that when the dimension of the data is small, let's say is equal to 1 or 2, KNN is outperforming, look at that, the green dashed line. This is MSE in the test set using KNN. KNN is outperforming the simple OLS when dimensionality of the data is small. So it's completely outperforming here. Here is completely outperforming when dimension is equal to 2. KNN is completely outperforming when dimension is equal to 3. For some values of k, the KNN is outperforming, and when dimension is 4, well, for some values, they're equally performing, KNN and OLS. So it seems that when the dimension of the data is small, right, let's say 1, 2, 3, and you know that the true relationship is nonlinear. So let me summarize it like this. If you know that there is nonlinear relationship in the data, plus the dimensionality of the data is low, so low dimension, then you may prefer KNN to simple OLS, simple regression model. However, when the dimension of the data increase, let's say 10, 20, as you can see, regardless of the value that you pick for k, KNN is going to do a very worse job compared to simple OLS. So OLS is completely outperforming KNN when the dimension of the data is large. So in this example, 10, even when dimension is 10, the OLS is outperforming the KNN by large margin. So these are the MSE numbers, right? The smaller the better. Okay, so that's why we should be careful when you're applying KNN models both for classification and regression. Especially for regression, if the dimension of the data is large, we know that there are better machine learning models out there, so we should not necessarily waste time using KNN regression. All right. Let's talk about KNN's pros and cons, starting with the advantages. So KNN is a very intuitive and simple model. We already talked about the algorithm, both for classification and regression, and we know that it's very simple to implement. It's a non-parametric model. It means that there's no assumption. If you're not going to impose any functional form or assumption on the distribution of the data, right? It is easy to implement for multi-class classification problems, right? So this is one of the biggest advantages of KNN. Let's say you have 4 classes, 5 classes. You can easily apply KNN to find the cloud of data, basically to figure out what is the pattern in the data. It is used for both for classification and regression, and then the other advantage is that there are very few parameters or hyperparameters. Basically, most of the time we're dealing with distance metrics and number of neighbors. Okay, so these are the advantages. So in terms of disadvantages, we know that KNN is slow, so it's a memory-based approach. This means that to classify new data points, the KNN algorithm reads through the entire data set to find out the k nearest neighbors. So we talked about this lazy learner approach aspect of KNN. Okay. And the next disadvantage is scarce of dimensionality, and we saw that especially in regression analysis, when the dimension of the data is not that large, basically if it is only 10, then KNN is not even beating the simple OLS regression model. Okay. So it is also not good with multiple categorical features, and the reason is that when we have multiple categorical features, then the choice of distance metric is going to become very subjective, right? Should we use Euclidean distance? Should we use Manhattan distance? And we're going to see that the answer is going to be, in some cases, very different from each other because we are dealing with multiple categorical variables, and calculating the distance is going to become subjective. And another disadvantage is choice of k. basically we know that K must be pre-specified before starting to generate the outcomes. However, this is not necessarily a big deal because we can always use cross-validation and tune the hyperparameters. Finally, so maybe this is a big deal when it comes to using, either you want to use KNN model or not, because KNN is a non-parametric model, and absolutely we cannot use it for interpretation. There is no interpretation, none, right? There is no parameters that you can interpret it at the end of the day. So if you want to use the machine learning models and also at the same time think about interpretability of that model, KNN maybe, especially for regression, is your last option. So here's my final thought about KNN. KNN is mostly used for classification. So if you want to do regression analysis with KNN, you would be better off using other models, other machine learning models. But for classification, we know that KNN is a very robust classifier, especially when the dimension of the data is not that large. So for that reason, it is often used as a benchmark for more complex classifiers, such as even artificial neural networks or support vector machines. Okay, so let's wrap up this episode by going over some of the KNN applications in finance. So the general idea is that you want to classify a new observations in the test set by looking at its similarities, the distance, the similarities of that observation with other observations in the train set. Okay, so just keep in mind, KNN is mostly used for classification. And when it's come to regression, we know that there are better machine learning models out there. So this is number one. Number two is that as long as you can keep the size of the dimension of the data set manageable, let's say 20, 30, 40, then you can think of KNN. If your data set by nature has hundreds or thousands of features, then you should not necessarily invest your time in using KNN as a classification. So all these examples that I'm going to show you down the road are going to be examples for classification, and we assume that the dimensionality of the data is a manageable number, maybe at most around 30. Okay, so let's start. The first one is, for example, you want to use KNN to classify bankruptcy predictions, right? So we know that, remember, KNN, the output is probabilistic. So we can say by looking at the financial ratios of a company, we can come up with some probabilities that if that company is going to become bankrupt or not, right? Then another example is stock price prediction. So we're not necessarily interested in the level of a stock. We are looking at the sign of the bet, right? So let's say buy or sell or hold. And just here, I want you to remember that don't get super excited with stock price prediction in general when it comes to machine learning, because the best accuracy we can get is around 53, 54% with KNN in literature. And this is what we get is about the sign of the bet. We can say buy or sell. We cannot say anything about the size of the bet. Okay, now buy, but how much? Sell, how much? How many shares, right? So this is basically talking about finding the sign of the bet. Then the next example is corporate bond credit rating assignments. So imagine you want to specify if a company that is issuing a corporate bond, the bond is going to be investment grade or let's say junk bond, right? So, or maybe you can say you can classify the corporate bond ratings into 5 different classes, 6 different classes, right? AAA, AA, and etc., right? So in these examples, when the dimension of the data is relatively small and you have multiple classes, let's say 5, let's say 10, then KNN is going to be a very attractive candidate. Next example, money laundering analysis. So imagine at the end of the day, you want to keep track of a transaction and then you flag it, is it a fraudulent or not? And next example is bank customer profiling. This is a very classical example for classification. So let's say you want to come up with 4 different classes for the customers of the bank, right? So because this is a multiple class classification, 4 classes, and the dimension of the data is usually manageable and small, 20 to 30, so why not using KNN? And actually we are going to see that KNN is going to do a good job for bank customer profiling. Another example, you can think of loan management. If you're a lender and you want to decide should you lend to someone or not, right? Again, in all these examples, the feature size is small and manageable. So that's why we can think of KNN as a classifier. Okay, this wraps up our module number 8, K-nearest neighbors. So in the next video, I will cover all these things in Python, and we're going to see how we can use scikit-learn and PyCaret for implementing KNN regression and classification models. Until the next one, take care.